Welcome. In this video we'll cover the modular structure of the FLINT. Displayed here is what a simulation landscape looks like in the GCBM. The landscape as a whole is divided into 1 degree by 1 degree square tiles, with each of those tiles divided into 100 0.1 degree blocks, which function as working units. Blocks are divided up into pixels of configurable size, less than or equal to 0.1 degrees. One difference between the FLINT and the CBM-CFS3 is that the CBM-CFS3 simulates the entire landscape one time step at a time, whereas the FLINT simulates 1 pixel at a time. As previously mentioned, this makes the FLINT very scalable, but it does make certain modeling problems difficult. For example, awareness of neighboring pixels when modeling fire spread, and processing rule-based disturbances where the exact location is unknown cannot be modeled. Displayed here is a very high-level overview of what this event-driven system looks like. Each pixel is simulated through its hold time series before moving on to the next. The pixel data is loaded, then a sequencer module undertakes a sequence of system lifecycle events that science modules subscribe to in order to do their processing. For example, the timing init event notifies modules when a new pixel is loaded, and then the timing events are looped over. The timing step start occurs at the beginning of the current time step. Timing step end occurs at the end of the current time step, and the output event is for any post-time step reporting. Note that the events shown here are only a subset of what actually occurs. One example of a module is the growth module. It subscribes to 3 of the system events mentioned on the previous slide. The simulation start loads the root biomass equations. Each time a pixel is loaded, it loads dead organic matter turnover rates, and the timing step loads and processes the current growth curve. The science of the CBM-CFS3 has been implemented as GCBM modules running on the FLINT platform. Ecosystem components including biomass, soil, and greenhouse gases are represented as carbon pools. As mentioned in the previous slide, it contains a yield curve-based growth module, and disturbances and annual processes are represented as transfers between carbon pools. The core modules include biomass growth and mortality, dead organic matter and soil dynamics, and disturbance impacts, which can include management activities like harvesting, natural disturbances like fire, and land use changes like deforestation and afforestation. Development of the FLINT and GCBM processes included validation of the results against a non-spatial model. When Canadian national-scale carbon results were compared between the GCBM and the CBM-CFS3, they were nearly identical. The main differences between the GCBM and the CBM-CFS3 are that in the GCBM, forest inventory and disturbance data must be spatial layers as opposed to database tables. The locations of all the disturbance events are explicit in the spatial layers instead of being rule-based. It produces spatial as well as tabular results output for pools and fluxes. It's easier to add new modules and easier to simulate very large landscapes, such as those with a large number of pixels. Displayed here is an animated example of one of the outputs, net primary productivity, generated using the GCBM. The simulation does not produce this kind of animation directly, but a set of Python scripts was developed to produce these outputs. Many scripts are freely available with the GCBM, including those that generate animations using the spatial output. In the next video, we'll look at the structure of a GCBM project.